When we actually tackle the problem of finding an approximation for the area under a graph, what we're going to find is that our approximations will be giant sums of numbers. So they'll look like some number plus some other number plus some other number, and just with lots and lots of terms, way more terms than we're going to want to write down. But all of the individual pieces of these giant sums that we have to write down will follow a pattern. So it would be really nice if we had some nice notation for writing down a big sum where each piece of the sum, each term, follows a pattern. And there is notation for that kind of situation. It's called sigma notation. So let's see how that works. So here's a big sum that follows a pattern. 2 times 1 plus 2 times 2 plus 2 times 3 plus 2 times 4 plus 2 times 5. Okay, you can see that the pattern that this follows is each term in this sum is 2 times some number. So this is the pattern that this sum follows. And all of the numbers that are being multiplied by 2 here, these start at 1 and then goes up by 1 in each term. And then the last term is when this gets up to 5. So here's the pattern. It starts at 1, goes up to 5, and every term in this sum, they're all added together. Okay, so this big sum, we could abbreviate it with all of this information. Well, this isn't much of an abbreviation because it actually took more time to write down than the sum that we started with, but let's just agree on some abbreviations for all of this stuff next to the bracket. So our pattern, we're going to write it like this: 2 times, instead of having a box, we're going to have a variable. And we could use any variable, x or n or I. I'm going to use I. I is sort of a traditional variable to use in this kind of context. N is another common choice. This is not the imaginary number I. It's just a variable. To indicate that all of these things that we're adding up, all of these terms are going to be added up, we're going to use a Greek capital sigma, because it's a Greek S essentially, and S is for sum. Okay, to indicate that the variable is I, we're going to put that right down here. To indicate that it starts at 1, we're going to write I equals 1 down here. And then to indicate that you go up to until I gets to 5, we're going to put a 5 up there. Okay, so this expression with the sigma is our abbreviation for this big sum. To make sure that we understand how this works, let's look at an example that I'll write out the sigma, and we'll write out all the terms of the sum together. So here's another expression with a sigma. So sigma I equals 2 to 4 I squared. So what is this? Well, remember, we get one term for every value of I, starting at 2 up to 4. So there's going to be an I equals 2 term. There's going to be an I equals 3 term. There's going to be an I equals 4 term. And then it stops because 4 is the last term. All of these terms are going to be added up. And to write out each term, we just use this pattern right here. This pattern says whatever I is, you square it. So in the I equals 2 term, I is 2, and that's going to get squared. In the I equals 3 term, I is 3, that gets squared. And in the I equals 4 term, I is 4, and that gets squared. And now this is just a big arithmetic problem. So 2 squared is 4, plus 9, plus 16. So 25 plus 4, 29, I guess. Okay, so that's how sigma works. You can see you can abbreviate really, really large sums using just a little bit of notation. So just an example of a really large sum, the sum from I equals 1 to, say, 100 of I, right? This is 1 plus 2 plus 3 plus 4 plus, and so on, all the way until you get up to plus 98 plus 99 plus 100. Right? I wouldn't want to write out this entire sum. It would take forever. But this sigma notation takes advantage of the fact that all of the terms follow a pattern to describe the entire sum just using the pattern. All right, so now we can express very large sums in very compact notation as long as there's some pattern we can follow. Now, one drawback of having extra notation like this is that new notation, every time you introduce new notation, it has its own algebra, really. So let me show you what I mean by this. Let's look at this sum. So 1 plus 2 plus 3. One way to write this using sigma notation is the sum from I equals 1 to 3 of I. Okay, well, let's suppose that we multiplied both sides of this equation by 2. That would look like this. Okay, so no big surprise here. But on the right-hand side, if we wanted to, we could distribute this 2, and then it would look like 2 times 1 plus 2 times 2 plus 2 times 3. And now it looks like the pattern is different, right? Originally, the pattern was just I, but now it looks like the pattern is, well, we should have had 2 times I, and I goes from 1 to 3. But that means that these two expressions with sigmas are actually the same. If you have a number multiplying outside of a sigma, you can move it inside of the sigma. You can see that when we have the sums written out here, this is really just distributing. So moving a constant multiple inside is just distributing, and moving a constant multiple outside is just factoring. But it looks different when we're using this new notation. So this is one fact to keep in mind. If you have any constant times a sum, and here for the terms of the sum, I'll write a sub I for I equals 1 to whatever the top happens to be, n maybe. You can move that constant multiple inside the sum like this. Okay, so there's a nice fact about sigma notation. Here's another pattern that sigma notation follows. So suppose we have two sums, so maybe 1 plus 2 plus 3 plus, say, 1 squared plus 2 squared plus 3 squared. So one way that we could write this is to use sigma notation. This first piece, we could write it as the sum from I equals 1 to 3 of I. And then the second piece, well, it's the same I values, still from 1 to 3, but the pattern is different. Instead of just being I, it's I squared. Okay, so this is one way we could write this sum using sigmas, but going back to the original line, another way that we could organize things is by pairing up these values that have the same number in them. So pair up the terms with 1s and pair up the terms with 2s, and that would give us 1 plus 1 squared, plus 2 squared, plus 3 squared. Right here, we've just used the fact that we can rearrange a sum. This is the associativity and commutativity of addition, essentially. But now, if we went to write this using sigma notation, the pattern would be different. The I values would be the same. We're still going from 1 to 3. But the pattern would be different. Now it looks like the pattern is, well, there's I plus the square of I, like this. And so what this whole thing shows us is that the sum from 1 to 3 of I plus I squared is the same as the original way we wrote it, which is the sum from I equals 1 to 3 of I plus the sum from I equals 1 to 3 of I squared. So it looks as if this sigma symbol here has distributed over the pattern, which isn't exactly what happened. Really, this is the associativity and commutativity of addition, but it looks as if the sigma has distributed. So we have a couple tricks we can use with sigmas now. If we have a constant multiple in front of a sigma, we can move that inside to the pattern, or if it's inside, we can move it outside. And also, if we have a sum in our pattern, we can split the sigma up at the sum, or distribute the sigma, sort of. Finally, there are a few formulas for nice sums that come up common enough that it's worth knowing the formulas. So one is, if we take the sum from I equals 1 to n of 1, well, let's write this one out. This is 1 plus 1 plus 1 plus, and so on. Right? All of the terms in this sum are 1, but how many times have we written down 1? Well, once for every integer from 1 up to n, so this is n times. And if you add 1 to itself n times, you get n. Okay, so this sum is just n. Another formula that's pretty nice to know is the sum from I equals 1 up to n of I. So this is 1 plus 2 plus 3 plus 4 and so on all the way up to n. Now this formula it's not obvious what you get here, but in fact you get n times n minus 1 over 2. There are lots of ways to see this, and I might post a video about why this is correct, but you can see this gives you a really quick way of adding up all of the integers from 1 up to any ending point you want. You just put your ending point into this formula and you get your total. The last one that I'm going to write down is the sum from I equals 1 to n of I squared. Now, in fact, there's a nice formula like this for any exponent in here, well, for any positive integer exponent in here, but we're only going to go up to the squared one. The formula for the sum from I equals 1 to n of I squared turns out to be a little more crazy. It's n times n plus 1 times 2n plus 1 all over 6. So there's some nice geometric arguments to see why this is the case, but we'll just take it for granted that this is the case when we go to use these sums. Oh, I'm sorry, this one right here should be plus. So we'll take these formulas for granted and use these when we try to find approximate areas.